Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. All right, gang, in this special bonus episode of the podcast, I'm joined by Ewin Tang, a PhD student in the Theoretical Computer Science group at the University of Washington. In our conversation, Ewin and I dig into her paper, A Quantum-Inspired Classical Algorithm for Recommendation Systems, which took the quantum computing community by storm last summer. Now, we haven't called out a Nerd Alert interview in quite a long time, but this interview inspired us to dust off that designation, so get your notepad ready. And now, on to the show. All right, everyone, I am on the line with Ewin Tang. Ewin is a PhD student at the University of Washington in the Theoretical Computer Science group. Ewin, welcome to This Week in Machine Learning and AI.
Hi, thanks for having me.
I'm really glad we finally got a chance to connect. I think I first reached out to you back in the summer when you came on my radar for your, I think it was your undergrad thesis around, was this like July or so?
Yeah, that sounds about right, yeah.
So I'm not going to explain it. I'm going to let you explain it. But before we do that, tell us a little bit about your background, what you're up to now, and how your interest in machine learning evolved.
Right now, I'm like a first-year grad student. So last year, and the 4 years before that, I was at the UT Austin, University of Texas at Austin, and initially, actually, starting my undergrad, I was a math major. So I was like interested in doing some like some much more theoretical stuff. But then I sort of realized sort of how interesting computer science was, and like how a lot of it is like has a lot more tangible applications that seem really interesting. And that's what led me to take Scott Aronson's course in quantum information theory, so quantum computing type stuff. And from there, I kind of just stumbled into the field of quantum machine learning. So I'd done a little bit of research in like machine learning type things, or sort of like the theoretical side. But this sort of work in quantum machine learning was just brought up because I wanted to do a thesis, an undergrad thesis advised by him, and then that was a problem that he suggested. And so that basically was, he sort of phrased it to me as like a problem of actually solving a lower bound. So technically it wouldn't have been like machine learning per se if I actually got that result. But since the result I got was an algorithm, it's now, I guess, kind of machine learning. But yeah, that basically started my interest in the field. I'm working on that a little bit here at UW, and I'm also working on some other things with my advisor, James Lee.
And so the headlines I remember from back in the summer were like this major kind of quantum computing advance, which I took to be that there were this class of quantum machine learning algorithms that were to a large degree considered to be a big part of the justification for quantum computing, at least by some people. And your thesis basically showed how, well, you didn't really need quantum computers to do this. Is that, how close is that to describing the thesis? And can you kind of put it in your own words and maybe give us an overview of it?
Yeah, that sounds actually pretty accurate. So, the general idea of my thesis is that there's this field of algorithms called like quantum algorithms, that solve machine learning tasks. And usually this is like very basic tasks like linear algebra type things. And the reason people were so excited about them when they were released is that they produce exponential speedups for these linear algebra problems. So basically, if you're familiar with quantum computing, the sort of the highest, the best type of speedup that you can get is an exponential speedup. And that's, for example, what we believe occurs for like factoring and like Shor's algorithm and the problems that quantum computing is known for solving. And so an exponential speedup would be great, but it kind of has some caveats in the sense that these algorithms assume some very strong assumptions about their input. Basically, they say, okay, if you give me all of the data in a quantum state, so that means like if you give me everything in like superposition, basically, then I can do it exponentially fast. Then I can, do your machine learning incredibly fast. However, doing this is actually creating these quantum states is actually a hard task computationally. And so people were kind of skeptical about whether you could actually implement these things. People weren't sure whether you could, whether even when the subroutines, when these like linear algebra routines are fast, that just getting to that point would take so much time that it wouldn't have been worth the effort to begin with. So that's the sort of conflict that's sort of motivating the work. So my thesis was about a particular algorithm. It's an algorithm by Jordan Karan-Nidison and Nupam Prakash called quantum recommendation systems. And it purports to like give an exponential speedup for the problem of like recommending products to users, like what Netflix or Amazon do. And the interesting thing about that algorithm is that it actually has relatively few assumptions. So it doesn't assume that you can just implement quantum states out of thin air. It gives like a protocol, it gives like a data structure for you to construct these things. And further, a lot of the previous quantum algorithms were sort of trying to solve problems that weren't being studied classically. So these previous quantum algorithms were just constructing problems that they believed could be solved faster with quantum computing, and then they justify their usefulness. But the nice thing about this algorithm is that it had been studied previously, and then people had not been able to get even close to as fast as what the quantum algorithm achieved. So basically, this recommendation system algorithm was one of the best examples of quantum machine learning that we had, and it was exponentially faster than all previous classical algorithms that we knew of.
Is this recommendation system or algorithm that they proposed, is it based on matrix factorization? And is that why did they kind of inherit the exponential speedup of some matrix factorization algorithms, or is there something kind of fundamental to their approach that gave them that exponential speedup?
Yeah. So it's basically like matrix factorization. Yeah, it's essentially what happens is that you want so your recommendation matrix is some like low rank matrix, basically, that just the implication is that people base their preferences on some small number of attributes that something has. So maybe you judge an Amazon product by its popularity, its price, and then the number of stars or something. And so you have relatively few attributes, which tends to lead to low rank matrices. And the general idea is that you want to factor this matrix, like compute the SVD, and this will separate your users into user classes, basically. So you can say, okay, these are like prototypical users, and then these are sort of recommendations for prototypical users. And thereby, if you give me a user, I can look at it and say, how similar is it to these users that I already know the recommendations for, and then compute the recommendations accordingly. Mm-hmm. And so this is basically what the quantum recommendation system does. It does all of this in like the quantum like superposition world. Like it doesn't actually explicitly write down any of these things, but it's able to do that without writing anything down. And so it can do it a lot faster than it would be to write anything down.
So I'm curious, maybe we can hit pause on the thesis conversation. I've had several interviews about quantum stuff. And yeah, to be honest, I don't really understand it still. And so that's probably the case for at least a few people in the audience as well. I'm curious, in your words, like, how do you think of this whole quantum computing stuff? Like, how do you explain it to people?
It's kind of hard because I'm not really that good at like quantum computing intuition myself. So I think the way that I like to think about it, at least when I'm like, at least that the way that it's relevant to my research is that it's useful to think of like quantum superposition. Like if you think of like saying a quantum superposition over states, usually you can like pretty well approximate the meaning by replacing like quantum superposition with probability distribution.
Mm-hmm.
So like generally what I like to do is whenever I hear about like quantum computing is just about setting up these probability distributions in the right way. And these probability distributions are souped up so that you can have these like interference. So you can have probabilities cancel each other out. Yeah. And basically, it seems like a lot of the like exponential type speedups, especially, come from this type of like way of thinking about it.
So roughly, we can think of a computer that's made up of not buses and cells and gates that deal with ones and zeros, but rather those similar kinds of things that deal with probability distributions and weird ones that interact in weird ways.
Right. So, if you think about so it's useful a lot to think of like, okay, like a probability, like a quantum superposition of 0 and 1 is essentially just like a probability distribution, like a coin flip, picking 0 or 1 each half the time.
Mm-hmm.
And obviously this fails sometimes because whenever you want to like do some cancellation, you might have a situation where you technically it's okay. So you have a 1/4 probability of one thing, and then you add that to a 1/4 probability of the same thing, and then you get 0 somehow. But a lot of the techniques that are used in quantum computing are basically similar to their like classical analogs, similar to what you would do to manipulate probability distributions.
And so then back to your thesis, there's this recommendation algorithm based on matrix factorization, and you started out by trying to identify what?
Initially, we believed that the quantum algorithm that they provided, that the quantum recommendation system algorithm, you could prove that it was exponentially faster than any classical algorithm. And so what this would do is basically show, hey, we found an example where quantum can help exponentially in machine learning. And so this is something that people had already believed.
So there was an existing proof that this algorithm couldn't be done in classical computers?
We wanted to show such a proof. We wanted to,
got it.
Yeah. We wanted to actually show that you cannot do the same thing classically, and people sort of already believed this because of how strong the results looked, and so this would have been like the final nail in the coffin. But the thing is that, well, I worked on it for a while and I kind of got nowhere. So like this was for my undergrad thesis, so I guess I had 9-10 months to solve it, and like halfway through I had nothing. I didn't have any approach to a lower bound. The things that I tried didn't seem to work, and gradually I came to realize that the reason the strategies didn't work was because the recommendation algorithm can actually be mimicked with a classical algorithm.
What was it that told you that?
There are a couple of factors that led me to realize this. So the first factor was basically that whenever I tried to prove some sort of lower bound, tried to prove that classical algorithms couldn't do the problem, I would run into some sort of roadblock. And then in analyzing what these roadblocks were further, I could basically sort of figure out what were the parts that seemed that the classical algorithm could do. So it's kind of like a push and pull. If you want to design a classical algorithm, you have to try to do it without hitting any roadblocks, because the problems that you come up with are hard. Whereas if you're trying to prove a lower bound, you're trying to show hardness. The roadblocks are actually things that a classical algorithm would find easy. Essentially, all of the roadblocks that I found were basically were indications for what could be done for a classical algorithm, and so that was one factor. Basically, just that research into lower bounds gives you some understanding of like where the hardness of the problem is and how you could avoid it. And the other factor was I early into the research, I found this paper it's Alan Fries, Ravi Kannan, and Santosh Vempala. It's a machine learning type algorithm. Basically, it does low rank matrix factorization, and it does it in time independent of the input size. So basically what that means is like no matter the dimension, it can do it just as fast. And it does this with some assumptions. So it assumes that you can sample somehow from the entries of this input matrix. And the interesting thing is that these input assumptions, these sampling assumptions that are crucial for the algorithm, were also present for the recommendation system model. So you recall that we don't get the matrix just to like read from, like we don't just get like random access memory to the matrix, the matrix that contains like user product preferences. We also get it in a data structure. So in order for the quantum algorithm to be able to prepare the superpositions that it wants, it designs a data structure. And this data structure classically also allows for you to perform the exact type of samples that you would need to do this fast classical algorithm. Now, just from this algorithm, it's not obvious at all what really to do with it. It kind of shows that you could do it, and then you could factor the matrix and stops there, when in fact for the recommendation system problem, you need to do something with those vectors that you find. And it's not obvious how you would do that, but it was an indication that said, okay, you can do some things in this model. Some of the tasks that you might have thought were hard classically, you might need to rethink those problems.
So a big part of your thesis was coming up with this classical algorithm that was analogous to this quantum algorithm. And you mentioned that you'd found some prior work that had similar constraints as the algorithm did in the quantum side. What did you need to do to get from the prior work to the algorithm that corresponded to the quantum side?
So it's kind of interesting. I wasn't familiar with any of this, so this is like in the area of like theoretical recommendation system literature. There's this set of papers that basically talk about how to like theoretically model recommendation systems and do like that sort of analysis. And so they use the name recommendation system instead of like, I think people use collaborative filtering more recently. Does that sound right?
Mm-hmm.
But yeah, so there were a set of papers that basically in like the early 2000s to late 90s that basically laid out the entire model for recommendation systems. And this is the model that is used for my algorithm and for the quantum algorithm as well. And they actually came up with something. It's basically the same thing as what Fries, Kannan, and Vempala did. They basically found this prior work and then sort of got stuck because what you have to do is just to lay out the groundwork. What we want to do is we want to give a sublinear algorithm for this recommendation system problem. And because it is a sublinear algorithm, this means that we can't read all of the matrix in, all of the input in. And so if you imagine your input as being a set of preferences that users have for particular products, it even means that we can't list out all of the uses that we have or list out all of the products we have. We don't have enough time to do that because we want to give like a logarithmic time algorithm. It's the time that we are allotted is so small that we can't do much. And the problem with that is that we're dealing with like a linear algebra problem. And so what this prior work outputs is it outputs the singular vectors of the input matrix. But it can't output the singular vectors because the vectors are the length of the matrix. And so you can't do that in enough time. Does that make sense?
I think so, yeah.
Yeah, so you don't have enough time to output the whole vector. So you have to describe what the vector looks like. You have to give what they call a succinct description. And so what they do is they can't say, here's the vector that we give as output, because to write out all of that down, it takes too long. Instead, what you say, look at this set of users and then perform some sort of like linear combination or some like you do some vector addition or something on these users. And that's going to be your singular vector. So you've described the vector that you want to output based on the vectors that you were given. And that way you can avoid the whole process of giving out each entry one by one. But that's a problem if you actually want to use this result, because now you can't actually read the vector. You have to deal with all of this stuff beforehand, and that stuff takes a lot of time, presumably, right? And essentially, you run into this issue where you really want to write your vectors down, but you can't because you don't have enough time. And the quantum algorithm sort of forgoes this issue by just having everything in a quantum state. And so if you have something in like a quantum superposition or something like that, you don't have to write anything down. So that was the main issue from going from the prior work to the recommendation system algorithm. And so what I ended up doing is figuring out, okay, you can avoid this problem by looking at by taking quantum superpositions. And so maybe you can actually do the same thing with the distribution. So you can avoid the problem of writing everything down by using a probability distribution. And what I mean by that is basically to say the following. Using the fact that we can sample high weight entries of basically anything that we want about the input matrix. So, I can get the user product preferences that matter most. I can sample randomly. So I can just pick a bunch of random samples from the matrix, from the input matrix, and use that to give a decent approximation of the vectors that I want. What's interesting is that basically you can do this through the entire process. So basically, once you have this succinct description, you can actually use that for sampling. So even though I haven't written anything down about the vector, I can actually still sample from it. It's basically not obvious, but you can actually do it. And so once you have these samples, you can sample from the high weight entries of these vectors. You can go the rest of the way. You can do whatever you want to do. And for the recommendation system case, basically what you want to do is you want to perform some projection operation. You want to project your user vector onto these matrix singular vectors. And it turns out that you can do that using these like sampling strategies. And that basically gives you the algorithm. You can do everything without writing anything down, and so you take like polylogarithmic time. So you take a sublinear amount of time.
The quantum algorithm is, you said, invariant with the length, so it's like big O of 1 kind of time for this recommendation system, and so you needed to do it in something sublinear?
Right. So the quantum algorithm is like big O of log n, something like that.
Okay.
So that's like logarithmic time. Anything that's like that to some power is like called polylogarithmic time. So what we achieve is we achieve polylogarithmic time. So we achieve something like log n squared or cubed or something like that.
Okay.
Initially, we thought that the quantum algorithm could do log n and the classical algorithm could do only like O of n.
Mm-hmm.
And so I brought the time down from O of n to O of like log squared n. So it's like a like exponential improvement.
And is this something that you envision would actually be used or deployed in some recommendation system, or is it more the kind of theoretical implementations on the what it means for this quantum algorithm and the theoretical analysis of this classical algorithm?
I mean, I certainly hope it could be useful in the future. So the thing is, like, because this algorithm wasn't really intended to be like, it was just something that I like hacked together in it, like, because for my theoretical purposes, anything that's like even close to the quantum algorithm would have worked. So I didn't think that hard about trying to optimize everything about the algorithm. So I'm not sure if it would actually work in practice. It's something that I still want to try to figure out. But I do think that it would be possible for somebody to like clean up the algorithm and actually get a version that works a lot better and then maybe is competitive with other techniques. I think what's done in practice right now is sort of limited by the amount of time that these factorization techniques take. So I think if you look at like what recommendation systems do in practice, they have to like update regularly. So they have to perform the algorithm every every week or every, I don't know how often they do it, but because you have to take so much time out to actually just sit down and compute the things that you want to compute, it just if you could speed up that problem, you could probably help a lot with the flow of the, I guess, recommendation system. I guess I guess I'm not the right person to ask about like the classical what it means for like practice. But I can at least say that for the quantum machine learning side of things, it's pretty interesting that you can actually just simulate all of these things with simulate all of these quantum algorithms with classical sampling techniques.
And did you a big part of your algorithm is replacing knowing the input vector with the distribution of the input vector. Did you characterize at all how that replacement impacts the ultimate results or performance of the recommendation system? I guess my thinking is that when you replace the full vector with some distribution, that's essentially like injecting noise or adding noise to this recommendation system.
Yeah.
And I'm just wondering if you looked at all at what the impact of that noise is on the performance of the recommendation system theoretically.
Actually, so the noise is quite bad from a theoretical perspective. So in fact, the sampling algorithm that I mentioned, the classical sampling algorithm, the prior work, was released in, I believe, 2007. And since then, there have been a lot of like improvements on this algorithm that basically say, okay, these sampling assumptions were too weak because they added too much. They sort of we can basically do better just by assuming a little bit more. And so a lot of these more recent algorithms follow the line of, okay, let's assume that our matrix is sparse, or okay, let's assume that we're able to read our matrix with some number of times. So like we're basically streamed all of the matrix entries, and then we're supposed to develop an algorithm off of that. And so in these models, you can actually you can improve your error quite a bit. It turns out that for the recommendation system problem, a lot of noise is okay. But that's also kind of just because we have strong assumptions for how good our data is. So even way back in like 2002, we had to assume theoretically that our data was really, really nice in order for us to give any recommendation algorithm. So we're still kind of operating off of some of these assumptions. So like if you look at my paper, like there are a lot of really weird assumptions that I have to cover in like the first 10 pages just to like sort of set the groundwork. And these are things that you could weaken presumably, or that you would have to weaken in practice. And so I'm not sure how the noise would impact that. It's not something that I've looked at, but it does impact it quite a bit.
And do you have a sense for the ultimate impact on the quantum machine learning kind of community or research based on the results that you came up with?
So there have been a couple of developments since this paper actually. Since this algorithm was, okay, I call it like dequantized, basically. I mean, like you took the quantum out of it, right? So you gave a classical algorithm corresponding to it. There have been 3 more quantum machine learning algorithms that have been essentially like this kind of dequantized, that have been dequantized. So I guess to like a bystander, it looks like quantum machine learning is like burning to the ground or something. Like like all of these algorithms are going down one by one. But I think I've talked to like some quantum machine learning researchers who were like who basically said, yeah, we didn't really believe that these algorithms were that strong anyway. So it's good that you're showing that that these are being dequantized, because essentially there is a lot of hype in quantum machine learning, and these hype is spurred by papers that claim a lot of exponential speedups. And so basically these classical algorithms, there have been some classical algorithms that try to say, okay, these exponential speedups seem really hard to achieve in practice just because these are easy tasks classically anyways. So you'd have to basically there should be like something stronger that you can do quantumly, or in order to actually get a exponential speedup that's I guess stronger. Like depending on what your model is, some exponential speedups are weaker and some are stronger, I guess. And so we're just right now, I guess this work has sort of served to separate some of the wheat from the chaff, I guess.
Are there currently existing strong use cases for these quantum algorithms or strong algorithms, or are these, have we dequantized a bunch of them, and do we need to now find the new strong cases?
I think that question, like the answer to that question, definitely depends on it's like an ongoing topic of discussion. So I think personally, I don't think that there's any quantum machine learning algorithm that has like a strong theoretical backing for being good, for giving exponential speedups. But I don't know, maybe that could change depending on the day. There is one algorithm. There's still hope, and that hope is because a lot of the algorithms that remain are based on this procedure for matrix inversion. So you may have heard of this quantum algorithm by Harrow, Hasidim, and Lloyd that inverts a matrix in time polylogarithmic in the dimension. And this algorithm is actually, it's what we call BQP complete. So this is like a complexity class that basically says, if you can dequantize this algorithm, then you can dequantize all of quantum computing. And so basically, we believe it's hard. We believe it actually does give exponential speedups in like certain circumstances. However, the thing is that the the situations for which we can devise exponential speedups are very contrived. So, if your input data happens to be exactly this matrix, then you can get an exponential speedup, for example. But of course, in practice, you want to be able to apply this to just any matrix that you have. And we know for a fact that, or essentially, we can't do this for any arbitrary matrix. We can't get a speedup for any matrix. At least it doesn't seem that way right now. And so it's kind of like a balancing act. So you have to try to find like the machine learning problem that's just hard enough to be out of reach for classical computers, but not too hard so that quantum computers can't solve them. So you need to be in like that sweet spot. And I guess the final thing is that even if we could find such a thing, the work would still be somewhat speculative because we don't actually know whether we can build quantum memory. So right now we have quantum computers and they can like do circuits and things like that. But for a lot of these machine learning algorithms to work, we assume that we have some really strong, like, I guess the RAM, they call it quantum RAM, QRAM. We have some really strong RAM that holds all our data and that we can do some like, we can query to and construct states from quickly. And so this additionally is something that we don't know whether it works in practice. So it works for classical computers, but we're not sure whether it works for quantum computers. And this is something that an experimentalist would have to confirm, I guess. It's all a little bit speculative, but it's interesting to think about all the different scenarios that could happen.
Right. It sounds like it's, considering that so many of these algorithms have been dequantized in just a few months since your paper was published. It sounds like it's a very fast-moving area, and I didn't realize that when we talk about these quantum algorithms and quantum computers that there's this huge missing piece, which is this quantum RAM. I didn't realize that wasn't part of what when we talk about quantum computers, that wasn't more of a complete package. But it sounds like there's still a ton of work to do in this space.
Right. It's interesting, actually. Like some quantum algorithms don't need memory, if that makes sense. So for example, you can run Shor's algorithm without requiring memory, because basically you can, for whatever number I give you, you can give me a circuit or a quantum circuit that basically simulates the RAM. So I can you can give me the input and I can construct the RAM quickly. So let's say like you gave me a number 4 and you wanted me to construct it. Well, basically what I can do in the terms of like what we care about for like quantum algorithms, what you can do is just devise a circuit that just outputs 4.
It sounds like you're saying that we kind of cheat, right? Like if you have some given number or vector, you could show that there exists some quantum circuit, that could serve as a RAM that will return this, that could store this number, but we don't really have a fully functioning system for getting that number into memory and then retrieving it back.
Right. Basically what I'm saying is like you can hard code it in.
Yeah.
Yeah. And the thing is that for algorithms that are faster than like O of n, so they're sublinear algorithms, you can't hard code something like that in because it takes too much time to read it. And so you really need the RAM. Whereas for other algorithms, you maybe can get away without using the RAM.
Well, awesome. Ewin, thanks so much for taking the time to walk me through what you've done and kind of the broader implications. It's, as we've just said, it's an interesting space. And because of that, I'll keep kind of coming back to it and, banging my head against it a little bit and see if anything manages to permeate. But certainly what you've done, you got a lot of publicity for your results back in the summer, and it's really interesting work, and I appreciate you taking the time to walk us through it.
Yeah, no problem. Thanks for having me.
All right, everyone, that's our show for today. For more information on Ewin or any of the topics covered in this episode, visit TWiMLAI.com/talk/246. As always, thanks so much for listening, and catch you next time.